So here we are back with our 2-atom molecule. This time I'm letting it fall down under the influence of gravity. I've not given it a motion in the x direction quite yet. And what we've got here in the graph is a look at the position of the center of mass of this molecule. So the atoms themselves are relative to each other, oscillating up and down a little bit. But the center of mass, you can see, is following a parabola in free fall, just like you would expect. Because the center of mass always obeys the same laws that a point particle will, which is why it's valuable to study that stuff, even if nothing is strictly a point particle in the macroscopic world. So we got the same kind of setup as before. We got our green atom and our red atom. We've got all the same stuff set up here. The thing that I've added in this case is a calculation of the center of mass. And so the way we're calculating this is a vector that keeps track of the center of mass position. And basically the way you do that, no matter how many particles you have, you can do this with 1,000,000 particles if you want. You just take each mass, so here I've got green dot mass, you multiply that mass times the thing's position, so green dot pos in this case, and then you just do that for every single atom, for every single particle in your extended object that you're working with, and you add those together. So here I've got plus red dot mass times red dot pos. If I added another atom to this molecule, if I added a blue one, I would just add plus blue dot mass times blue dot pos. And if I added a cyan one, plus cyan dot mass times cyan dot pos. Over and over and over again. You just keep repeating that process for every particle that you have in the system. And then you just divide it by the total mass. And you know how to get a total, right? You just add up all of this stuff together. And so dimensionally, your units for mass cancel, because up here you have units of mass times position. Down here you have units of mass, so your units of mass cancel. The masses do not cancel because algebra doesn't work that way, but the units of mass cancel. You're left with a position vector, and so this is the position of the center of mass. And so then here we're just creating the center of mass. Let's give this thing a label and call it center of mass, and this is actually going to be the y, because we're only keeping track of the y right now. So actually, let me change this COM graph to COM graph y. There we go. And let's be proper physicists and label our axes. So let's have graph here, and then our x title will be time, and our y title will be position. There we go. And so basically what we do down here in the loop, we've got the same kind of animation we had before. Again, the only thing we're adding is the stuff about the center of mass. And let's say update COM, end time, and repeat. There we go. And so here we're doing the same calculation. So basically in each instance of the animation, the center of mass is always given by this formula. So each of these values changes, but the formula doesn't change. So we just have to apply the same formula repeatedly each frame so that this thing can be kept up to date. So the center mass can be kept up to date. And then here we've got the COM graph, and we're going to change that to COM graph y. And then we've got t comma com.y. Actually, since making this code, I learned that you don't have to have the POS equals on there. You can just have the independent variable comma dependent variable, which is a lot easier, I think. And so when we run this, you know, the COM doesn't actually impact any of the animation up here. The red and the green are still being animated based on the Euler-Crömer method up here. What the COM is really doing is just giving us this position graph down here. And so we've got this piece here where we're following free fall motion. And so to test that, what I thought we could do for the rest of this video is add in some X motion. So let's give one of these folks an X velocity. Last time we gave the green a momentum of +1 in the X direction. Let's try giving red a momentum of -1 in the X direction, just to make this a little more interesting. And so we want to have that motion. We also want to be able to look at it on the graph. So let's do this, say copy and paste, and we'll just change these Y's into X's. And it's going to bother me if Y comes before X. There we go, alphabetical order, very nice, very nice. And then down here, all we have to do is copy this, paste, and then change these Y's into X's as well. Because the COM, remember, is a vector, right? It's got all the position information. You could even add some motion in the Z direction if you wanted to, and then have a graph of X, Y, and Z. I don't know that it adds anything to do that, but you certainly can if you want to. So let's see what happens here. So this thing is obeying constant acceleration motion going down, there are no external forces acting in the x direction. There's only the internal force of this thing, but the center of mass isn't going to experience any x forces, so we should get a constant velocity in the x direction for the center of mass. And I should have given these folks different colors. Let's try giving this one a color red. Some of y'all were shouting at me about that, I'm sure. There we go. So our center... Oh, yeah. So our center of mass in the y direction is falling like it did before. So we're accelerating in the y direction. In the x direction, we've got a constant velocity. This thing is moving with a constant... The graph has a constant slope, so that means our x coordinate has a constant velocity, which is exactly what we would expect. But we can check the velocity directly if we would like to. The way you can get the velocity of the center of mass is to basically use the same equation that you have here. So let's set up, copy and paste. We're going to set up velocity of the center of mass. Basically, all you have to do is replace these POS values, the positions, with the velocities. So let's do, all right, let's do the momentum here. So the way you get momentum, or the way you get velocity, is to divide by the mass. So really all we need to do is get rid of these masses here. There we go. So that'll give us the velocity of the center of mass. So let's do copy and paste down here to get velocity of the center of mass. And then what I can do is I can create a new graph of the velocities here, or the velocity of the center of mass. So let's see. I need to copy all three of these lines, paste them here. And so let's say graph time and velocity. And basically the way this is going to work, these two G-curves get created in this graphing window because this was the latest graphing window that was created. But these two are going to get created in this graphing window because it was the latest that was created. If you want to make that explicit, you can give each of these graphs a name. And then in the arguments here, you can say graph equals the name of that graph. But you technically don't have to do that if you get them all in order like this. Okay, so let's call this one VCOM graph X and VCOM graph Y. We'll have center of mass Vx and Vy. And we've called this one velocity there, right? Okay, cool. So I just need to copy and paste everything about these and add V's in front of them. So let's see. So now I need to take these two pieces, copy and paste. VCOM, VCOM. And then here I need VCOM.x and VCOM.y. And those will have the same colors there. You know what? Actually, let me change this from a red to, let's go purple again. Copy and paste. Just because we already have a red thing on here and I don't want us to visually associate those mistakenly. Okay, and here we go. We've got our center of mass Y and our center of mass X moving along like we thought they would. And here we've got our velocity in the x direction is the purple here. And so that is kept constant, like we expect. And here we've got the velocity of the center of mass in the y direction, which is decreasing steadily. So if you were to take the slope of this, it would be this value of the gravitational field, right? So we've got a change of, oh, let's go over to 10. That's easy. In the x direction, in the time axis. In the velocity axis, we've got a change of -1. So 1 divided by 10 gives you 0.1 right here, just like we expected. So there's a lot more you can do with the center of mass. You can get the momentum of the center of mass. You can get the kinetic energy of the center of mass. You can also graph their relative velocities and positions. So that's what you'll do for the follow-up problems at the end of the video. Again, thank you so much for watching. I will see you next time. Bye-bye.